Nielsen. And we have 6 exciting presentations to go. And the first one is to be delivered by Branislav Todic, coming from Qatar, from Texas A&M University in Qatar. Please go ahead. There's a point of.
Okay, thank you for the introduction. Good day to everyone. Thank you for attending my talk. Today I'll be talking about some of our studies related to the effect of process conditions on the selectivity of Fischer Tropsch synthesis over cobalt catalyst, and the importance that methane formation has on the selectivity of Fischer Tropsch. So do you switch the slides? Okay, so we had a couple of talks this morning about Fischer Tropsch, but I still think kind of an introduction is in order. So Fischer Tropsch synthesis is heterogeneously catalyzed reaction in which CO and hydrogen react over metallic catalyst to form an array of hydrocarbon products. Here we have general stoichiometric equations for the main products that are normal paraffins and 1-olefins. In addition to those, we also have a number of minor products such as 2-olefins, oxygenates, branched hydrocarbons also. The mechanism of the reaction is quite complex, and it is still under a lot of debate, but what is generally accepted is that Fischer Tropsch is a polymerization type reaction in which we have this initiation step. Then we have also propagation, in which this C1 monomeric species is built into the growing chain, and then we have the termination reactions to form our paraffin, olefin, and olefin. In addition to those primary reactions, we also have a number of secondary reactions. There we have the secondary reactions of initially formed 1-olefins, which are hydrogenation, isomerization to form 2-olefins, and then we also have the reabsorption and reincorporation into the chain growth. And also, I'll be talking about how we believe that there's evidence for a second pathway for the formation of methane, which we think is relevant in terms of reaction selectivity. So this study was a collaborative effort from my university, Texas A&M at Qatar, and the Center for Applied Energy Research of the University of Kentucky. The overall objective of the project was to analyze the kinetics of Fischer Tropsch synthesis over cobalt catalyst, and here I'll be talking mainly about this part where we analyze the effect of various process conditions such as temperature, pressure, feed ratio, and conversion level on selectivity, and we look at the parameters that are related to selectivity, such as chain growth probability and ratios of different product species. And using those, I'll try to draw conclusions about some of those primary and secondary reactions that I mentioned. So, as I said, Fischer Tropsch synthesis is considered to be a polymerization type reaction. So, initially the products of this reaction were explained with the so-called Anderson-Schultz-Flory distribution model, which is this, where molar fraction of hydrocarbon with N C atoms is described using a single parameter called chain growth probability. Now, if we linearize this equation, we can see in this plot down that products should obey this red dotted line, straight line. However, the actual product distribution typically deviates from it, and these deviations include high methane formation. We have low C2 due to low ethylene formation, and then we have this kind of a bend from the ASF where there is an increased amount of heavier products. So what this means is essentially that the alpha parameter is not constant, but it varies depending on the chain length. So we have a much lower growth probability of C1 intermediate, which is the source of methane. Then for C2, the growth probability is much higher. And then for the C3 plus, there's a steady increase with an asymptotic value in the area above C15. Here we also have a definition of alpha, which is essentially a ratio between the rate of propagation and the sum of propagation and termination. And this is why alpha is related to intrinsic kinetics, and by looking at how alpha changes at different conditions, we can make some conclusions about these rates of propagation and termination and their ratios. So here we see a Zephyr plot with main products, normal paraffin and one olefin. We see that essentially the slope of these two is different, and in some that causes the product distribution to deviate from the straight line ASF. If we plot the one olefin to paraffin ratio, we see that from C3 it essentially exponentially decreases with carbon number, and this happens at pretty much all of the conditions tested, and the dependency is usually around exponential negative 0.3 times n. So essentially, when we do Fischer Tropsch, what we want to get are the heavy products. The light products and methane are not desirable. So we try to look at this in a way to maximize C5 plus selectivity. And if we want to maximize C5 plus selectivity, we have to answer questions. First one being why is methane formation so much higher than what would be expected, and the second one is what is causing the higher than expected yield of these heavier products as well. Now, majority of research in the field was on the second question, because we do want to know primarily how to increase the formation of C5 plus. Relatively fewer papers have been published about methane formation. Now, regarding the second question, there have been several concepts proposed and used to explain this bend in the ASF. Initial one was the so-called double alpha model, in which it was assumed that there are actually two constant alpha values related to either the two types of active sites or the two reaction pathways. Now, the issue with this theory is that it wouldn't differentiate between the products. It was kind of lumping up hydrocarbons, and it couldn't explain why this exponential decrease in olefin to paraffin is happening. Then we also had some studies suggesting that kind of experimental artifacts are causing these deviations from alpha, and there might be some truth to that. The most accepted concept used to explain this behavior in the product distribution is the so-called olefin reabsorption theory, or I'll be referring to olefin reabsorption. When I say that, I mean reabsorption and incorporation into the continued chain growth. So the majority of studies kind of agreed that that this is the most likely cause, and there is some evidence for that in the co-feeding studies, olefin co-feeding. I will argue not enough evidence, and that additional theories should be considered. And one of those has been recently proposed in 2007 by Boats from Sassel. It's called chain length dependent olefin desorption. It's an idea that essentially the desorption step in the olefin formation is dependent on chain length due to the effect of some weak physical interactions on the chain. So in the study we performed a series of experiments in a stir tank slurry reactor. These were done at CAR in Kentucky. Very small particle sizes were used, and so that to avoid heat and mass transfer resistances, we used the rhenium-promoted cobalt catalyst with alumina support, and obtained data over a wide range of conditions, including 3 different temperatures, 2 pressures, 2 feed ratios, and a range of conversions. For CO conversion, it's from 18 to 62%. So now I'll be talking about the effect of various process conditions on selectivity. Now, if we fix the total pressure, feed ratio, and conversion level, and only vary the temperature from 205 to about 230 degrees Celsius, we get that with increase in temperature, we get an increase in selectivity of methane and light products as well, C2 to C4, and a decrease in the selectivity of heavier C5 plus products. If we look at how the chain growth probabilities with carbon number changed, we see that essentially alpha values decreased, and as I said, that can tell us something about rates of propagation and termination equation reactions. Essentially, what this kind of response to temperature would mean is that the activation temperature, activation energy of termination step is slightly higher than the activation of propagation step. Similarly, we observed a decrease in the olefin to paraffin ratio. It was a slight decrease, but it will also be explained with these observations with these differences in activation energies of secondary reactions compared to the termination and propagation, and this is in agreement with literature on olefin co-feeding. Now we looked at the effect of pressure. Pressure, we see that the selectivity to methane decreases as well as light products, and then we see an increase in heavier products. Now the possible factors that could play a role here at increased pressure are the decrease of hydrogen coverage, then also the higher partial pressures of 1-olefins, which would mean more secondary reactions, and also higher partial pressure of water, which could affect the also secondary reactions of olefins by inhibiting them. We observed that an interesting result that alkaline was relatively constant at 2 pressures. The only alpha value that increased relatively significantly was alpha 1. As for the effect of feed ratio, we did an experiment with constant temperature, pressure, and the relatively constant conversion level. I should note that essentially here the ratio of hydrogen to CO inside the reactor is not the same as the feed ratio, but in terms of our study that doesn't really matter that much, because there's a big difference between these, and so what we're comparing is low feed ratio or low hydrogen to CO compared to high hydrogen to CO. So if we increase the feed ratio, we see an increase in methane and light product selectivity, and a decrease in C5+. Interestingly, again, alpha values for C2 plus alpha was relatively constant, which is surprising, and the only big change, and a significant one, was for alpha 1, the growth probability of C1 intermediate. And what this caused in the product distribution, if you look at it, a kind of a shift downwards at increased feed ratio. As for the olefin to paraffin ratio, at increased feed ratio, there was a decrease in hydrogen, in olefin to paraffin ratio, which is consistent with higher reactivity in olefin hydrogenation reactions. Here we have the study on effect of conversion level at constant temperature, pressure, and feed ratio. This is here we see how methane decreases at increased conversion, same as the light product, while C5 plus increases, and this is something that is related to the olefin reabsorption concept, which I mentioned in the start. So the idea is that the olefins can go back, once they are initially formed, can go back to the active site and continue their growth, and the residence time of olefin plays a big role in that reaction, and the higher the residence time of olefin molecules inside the reactor allows for the higher probability of reabsorption events, and that's why the C5 plus selectivity should be increasing. Now, using that logic, we should also see an increase in the values of alpha n, or the growth probabilities. However, when we looked at those, we couldn't find clear evidence of clear increase. So the data was kind of around one range, but no particular trend. We did find clear evidence that olefin secondary reactions are happening because with higher conversion level, we saw much lower olefin to paraffin ratio. So these results meant that we need to ask certain important questions. For example, questions about olefin secondary reactions. What is the extent of these reactions, as well as selectivity, and how does that influences product distribution? Then we also had to try and explain why the methane formation is so high, and how to relate methane formation to the overall selectivity, as well as can we try to decrease the excess methane formation. Additional questions were related to the effect of water on product selectivity, and the reasons for increased growth probability with carbon number, as well as the olefin to paraffin decrease with the carbon number. So, so the first question was about secondary olefin reactions. Essentially, I said that before. There's three important secondary reactions: hydrogenation to form paraffin, isomerization to one olefin, and the reabsorption and continued chain growth. There has been a number of olefin co-feeding studies which provide direct measurements of these secondary reactions. The problem with those is the results are relatively inconsistent if you compare them. But that is mainly in terms of the amount of olefins converted. In terms of selectivity, they are somewhat consistent. Typically, they say that the hydrogenation is the most important one of these reactions, and then is followed by isomerization, and that the smallest amount of olefins is participating in reabsorption and incorporation. And this table is from Mani et al. That's one of CAR researchers who did experiments with labeled pentene. So we didn't do olefin co-feeding in our study, but we tried to analyze secondary reactions nonetheless in an indirect way. And so, as I said, we looked at the OPR and the alpha values, and one interesting plot that we got was the values of alpha for C1 and then C2, C3, and C2, C3, and C4 intermediates in Fischer Tropsch synthesis, and it changed. So the alpha values changed with conversions like this. Now, if you look at C2 plus, these values, they are relatively constant at different conditions. Now, this is changing conversion level, but these points come at different temperatures, pressures, feed ratio, and considering that huge range of data that we had, it's very interesting that we had such practically constant values of alpha for C2 plus, and the only one that seemed to change with process conditions significantly was alpha 1. Now this constant value of alpha C2 plus implies that olefin reabsorption in essence has a minor effect on the product distribution. If you look at the equations and the kinetic theory behind it. Whereas methane formation should then be much more important. And also what's relevant is that all these were relatively constant, whereas methane varied significantly, meaning that it exhibited a very different behavior compared to the other hydrocarbon intermediates, which suggests to us that there are different pathways involved in methane formation and not just the FTS pathway. So here we see a plot showing the relationship between these alpha values, alpha 1 to alpha 4, with the C5 plus selectivity. Again, we see that there is a correlation between all of them. Increasing any of the growth probabilities means you will increase the selectivity towards C5 plus. However, alpha 1 seems to be the most dominant one and the one that we can control the most and affect by our changes of process conditions. And so to understand how we can change alpha 1, one has to understand how methane is formed. And we looked at we analyzed how alpha 1 is affected by various changes of process conditions. So just singled out alpha 1 and only looked at it. We see that it decreases with temperature, it increases with pressure, it decreases with feed ratio, and it increases with conversion level. These are all the same trends of C5 plus selectivity. So I mentioned that in the past there hasn't been a lot of work on methane formation, methane being singled out, but there has been some ideas about why methane is different from the other products, and these ideas include high surface mobility of methane precursors and thermodynamic favorability of methane formation, then the hydrogenolysis of higher hydrocarbons by successive by removal of methane, then the lower activation energy for methane formation, and different pathways for methane formation, which could include both different sites for methane formation and, as displayed here, or just different pathways on the Fischer Tropsch active sites. And some work was done on that by Lee and Bartholomew, who hypothesized that absorbed CO and hydrogen absorbed from on the metallic sites can spill over onto the support and have some interactions there, building some intermediates that can diffuse back to the metallic surfaces and form this excess methane. But again, there's not enough literature on the topic to make a definitive conclusion on what is causing this excess methane formation. One interesting thing about selectivity is also that it seems that it is related to partial pressure of water. With increased partial pressure of water, we get increased C5 plus selectivity, and this could be related to this secondary pathway of forming methane, where this pathway could be inhibited by water. Now, a question that comes if we conclude that olefin reabsorption is not the cause of the non-ASF behavior, is what is the cause of this? And I mentioned one potential theory, recent one, chain length dependent olefin desorption, in which olefin molecules desorb with different activation energies, which is increasing with carbon number. And we did some modeling work on that and concluded that this increase in activation energy needs only to be about 1 kilojoule per mole per carbon atom for this to actually explain both the variation of alpha with carbon number as well as the olefin to paraffin ratio. However, other experimental issues cannot be neglected, such as the accumulation of products. There's been some recent work, again from CAER, that showed that there is an accumulation of products, and the actual product distribution we see, especially in the high carbon numbers, is not the real product distribution formed during that period inside the reactor. And so, to conclude, our study showed that the variation in selectivity of methane and C5+, with different process conditions, can be traced back to the changes in growth probability of C1 intermediate, and that chain growth probabilities of C2+ hydrocarbons don't significantly change with process conditions, which could suggest that olefin reabsorption plays a minor role in determining product distribution. And so understanding methane formation could really be the key to improving Fischer Tropsch selectivity. Thank you. I forgot to mention, to acknowledge the support of the Qatar National Research Fund.